Hey, we're back for the second part of 2.6. So we left off talking about resonance structures. Resonance structures are when you have equivalently correct atom arrangements, but we can move the electrons around into different places. The last example I went over in the prior portion was for this sort of situation where you do have different possible atom arrangements as well as different possible electron arrangements. And you need to determine which is the most valid structure. That's where this concept of formal charge comes in. Okay, so when, again, you have multiple possible structures where atoms are moved around and they still work out electron-wise, and we want to determine what's the best arrangement we can make, we use this concept of formal charge. It's not a real charge, so of course let's call it a formal charge. It's really just a bookkeeping system to make the most valid structure. It's used to determine the likelihood of a structure actually existing. It's very simple. The way that you would calculate formal charge for each particular atom in the structure by taking the number of valence electrons in that atom minus the number of bonds that you drew minus the number of dots that atom also has on it. And it will give you a number that's either positive, negative, or zero. Let's jump in. So we're going to draw the structure for POCl3 and assign formal charge for each atom in the molecule. So this goes back to Lewis structures. Phosphorus has 5 valence electrons. Oxygen has 6 valence electrons. Each chlorine has 7 valence electrons. So we have 32 electrons that have to go into this picture. So we'll put phosphorus in the middle, and we'll just kind of box it in here. We start by drawing in our bonds. Okay, so I just drew an 8. And then I have to fill in the octet for the peripheral atoms, and that takes care of all 24. If I still had electrons left over, it would be possible to put them on phosphorus because phosphorus is in the 3rd row. It can expand its octet. So now let's look at formal charge for each of these atoms. So formal charge is equal to valence electrons minus bonds drawn on that atom minus dots on that atom. Okay, so first I'm going to look at the formal charge of phosphorus. So phosphorus, following that sequence at the bottom here of the calculation, whoa, don't float around. Phosphorus has 5 valence, oh my goodness. Phosphorus has 5 valence electrons, minus how many bonds? I've got 4 bonds drawn on phosphorus, minus how many dots? I have 0 dots on phosphorus. So the formal charge on phosphorus is +1. Let's look at oxygen next. Valence electrons, it has 6. How many bonds are drawn on oxygen? 1 bond. How many dots are drawn on oxygen? 6 dots. So the formal charge for this would be -1. And then chlorine, each of these chlorines are identical, like their bonding is all identical, their dots are all identical, so I only have to do them one time. But if you had them bonded differently, you would have to calculate them differently. So chlorine has 7 valence electrons, minus 1 bond, minus 6 dots. So the formal charge on each of those chlorines is 0. So I'm going to write these numbers next to each of those elements. Okay, so those are the formal charges. Now, if this particular molecule doesn't have other possible valid arrangements, but if it did, you would calculate the formal charges on all of the atoms and all the possible arrangements, and I'm going to show you how to evaluate which one is the best. But that's the process. It's valence minus bonds minus dots. So for formal charge information here, atoms and molecules try, quote unquote, because they're not really trying, to achieve formal charges as close to 0 as possible. The sum of the formal charges of all atoms in a given molecule or ion must equal the overall charge on that species. So in this example, If we add up all the formal charges that we calculated, 0 plus 0 plus 0 plus positive 1 plus negative 1, it does equal 0. And this is a neutral molecule. There's no charge written there. So those formal charges are valid. Structures that obey the octet are always the best. Okay? So if you have the possibility of expanding the octet on one of these elements, like you could, but when you do formal charges, you always want to go with keeping the octet when possible. After that, if you have to expand the octet, the lower the formal charges, the better. So you want it to be as close to 0 as possible. The best Lewis structure is the one with the fewest non-zero charges, and it puts a negative formal charge on the most electronegative element. So in this case, I have only 2 non-zero formal charges, and the negative formal charge is on the most electronegative element. Oxygen has the highest electronegativity of those elements. So let's look at these structures from that last example to evaluate what would be the best. So the structure up top we have carbon, chlorine, and oxygen. So valence minus bonds minus dots. Chlorine, valence minus bonds minus dots. Oxygen, valence minus bonds minus dots. Okay, so that's this one. Okay, the one next to it, the chlorines are different, so I have to evaluate them separately. Carbon, valence minus bonds minus dots. Chlorine that's on the left is valence minus bonds minus dots. Chlorine that's on the right, valence minus bonds minus dots. Oxygen, valence minus bonds minus dots. Okay, so I have a non-zero number there. The bottom left here for carbon, valence minus bonds minus dots. I can't even do it. -3. Yeah, that's weird. Oxygen up top, valence minus bonds minus dots. Chlorine in the middle, valence minus bonds minus dots, +3. Chlorine that's on the right, valence minus bonds minus dots. You'll be singing this in your sleep. Okay, so we have these like random numbers for those and so on. So you would go through and evaluate each of these, and you want numbers as close to 0 as possible to get your most valid structure. You want them, and if you have non-zero charges, you want your most electronegative element to have the lowest formal charge. So let's look at these three possible arrangements, or 3 of these possible arrangements. This is, I think, the thiocyanate ion. So this is easier because we only have 3 to work through. So let's do nitrogen, 5 valence, -3 bonds, -2 dots. Carbon, 4 valence, -4 bonds, -0 dots. Sulfur, 6 valence, -1 bond, -6 dots is -1. So you see here, this ion has a -1 charge. So these formal charges need to add up to -1. Nitrogen, carbon, sulfur, nitrogen, carbon, sulfur. So 5 -1 -6, 4 -4 -0, 6 -3 -2. Oh, I'm sorry, this is -2. And that is +1. So we add all those up and we do get -1. And then 5 -2 -4. 4 minus 4 minus 0, oops, minus 0. 6 minus 2 minus 4. And those all add up to -1 as well. So which of these would be the best structure? We want as many values at 0 as we could possibly get. And we also want the element that has the most electronegative, so the highest electronegativity, to have the most negative formal charge. So that would give us the last one as the best option because we have multiple things close to 0 and a -1 formal charge on nitrogen, which has the highest electronegativity value. I don't know why I had that circled there. There we go. Oh, yours was already. Why do I have that circled? I cannot remember. Okay. We're going to do this XeO3. So there's that. So that's down to 20. That's 18. So there's 2 left, which go there. You could also exceed the octet. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Like this still works because xenon can expand its octet. So, and also I could have floated that double bond into the 3 separate locations. So let me show you how to do formal charges for this one on the left. All those oxygens are identically bonded, so we only have to do them once. So xenon, it has 8 valence electrons, minus 3 bonds, minus 2 dots. And then oxygen, 6 minus bonds, minus dots. And that happens 3 times. Am I mathing right? Valence minus bonds minus dots. Valence minus bonds minus dots. 2, 4, 6, 8, 10, 12, 14, 15, 16, 24. Something is wrong in my brain right now. We'll get back to that. And then this one, xenon, 8 minus 4 minus 2. Oxygen on the left, oxygen on the top, oxygen on the right. 6 minus 1 minus 6. The top, 6 minus 1 minus 6. And the one on the right, 6 minus 2 minus 4 is 0. I'm gonna have to go over this one in class with you because I can't get this straight in my head right now. Sorry. All right, let me show you this. We're not doing the bond angles yet. Let me show you this one. Lewis dot diagram for S2Cl2 by drawing in all the electron pairs. So sulfur, there are 6 valence electrons times 2. Chlorine, there are 7 times 2. So that's 26. 20. And then that leaves us with 8 left, because I said 12, so 2, 4, 6, 8. Simplest way to do this. We'll talk about bond angles later in the chapter. Okay, now here's one with formal charge. 2 possible structures for fulminic acid are shown below. Explain what the diagram is telling you. The diagram on the left is better, and it's asking you to justify based on formal charge. So, okay. On the left-hand side, hydrogen, valence minus bonds minus dots. Carbon, valence minus bonds minus dots. Nitrogen, valence minus bonds minus dots. Oxygen, valence, where's my valence? 6 minus bonds minus dots. Okay, on the right-hand side, valence minus bonds minus dots, valence minus bonds minus dots, valence minus bonds minus dots, valence minus bonds minus dots. Okay, so it's telling you the one on the left is better. So both of these, if we add up all the formal charges, we get 0 for both, which makes sense because they're molecules. But it's telling you the one on the left is better. So both of them have 2 0 formal charge elements, and they also have 2, like a +1 and a -1 formal charge elements. But the one on the left is better because oxygen has a higher electronegativity value than nitrogen does, or carbon or hydrogen. So oxygen should have the most negative formal charge, whereas in the one on the right, carbon has the lowest formal charge, and that's not correct because carbon does not have the highest electronegativity value. And we already did that one. So the goal with those 2 lessons was to work you through resonance structures and use the formal charge to determine which one's most valid. And also for bond order, that just means like if I have 3 resonance structures and I have a double bond floating between 3 of them, bond order would be approximately 1.3. We'll go over more of that in more detail.